So we got homework and quizzes going on this week. There is our next SI is on Monday, UTF's on hours tomorrow. So make sure that if you're still unsure of anything that was on that last exam, to get that all taken care of, right? Be solid on that before we go forward, even though, well, we're not going to do any more spectroscopy until the final anyway, I guess, but still. All right, so we have been talking about chemistry of benzene and aromatic compounds, right? Chapter 15, we talked about 5 different electrophilic aromatic substitution reactions. Okay, too much talking. We can put halogens on, we can put a nitro group on, we can put a sulfonic acid on, or we can put either an acyl group or an alkyl group. Okay, so now what we're doing in this chapter is we're going to go one step further and see what happens if we want to try to put another group on, or if we want to modify those groups. We want to make more complicated polysubstituted benzenes. So in chapter 16 so far, what we've really done is we did some naming, and then we started through looking at some of these different substituents that we already know how to put on and how we might modify them. So for example, we looked at halobenzenes, bromobenzene, chlorobenzene. Said main thing we could do at this point would be to make something like a Grignard reagent out of that, and then we can use that as a nucleophile and do whatever chemistry we want to do. We saw that we could take a nitro group, we could hydrogenate it down to an amine, down to aniline. What else did we look at? Sulfonic acid groups. If we heat them up in acid, we could take it back off. And then we started through alkyl groups. Just a sec here. So we looked at what we could do to toluene, so with just a methyl group. And the main thing we could do first was to put on a bromine, right? And then that bromine can either act as a normal alkyl halide, as an electrophile for substitution reactions, right? We can add groups and do SN2 substitutions, or we could convert that to a Grignard and use it as a nucleophile. All right, so I'm going to just add one more carbon on here, and we're going to see if we can think of anything else we could do in this case as well. So if we start with ethylbenzene, basically the first step we have is just the same as what we did before. So we could use NBS, and we could use HNu and peroxide, and we could brominate. Remember, this just brominates at the benzylic. Oops, I didn't do that right. At the benzylic position here. All right, so last time we saw we could do substitution reactions. We could convert it to a Grignard. Yeah, question?
Is this when we would use benzyl or in our
Mm-hmm.
You gave us benzyl and phenyl.
Right. So we used benzol, and phenol. If we were going to name this, I think we'd still name this as a benzene compound, but it would be a substitution. So it'd be an ethyl benzene with a bromo on it. So one bromo ethyl. So that'd be in parentheses benzene. Okay. So we could do the same chemistry with this. What else could we do in this case that we couldn't do with just benzyl bromide? Right, we could do an elimination reaction, right? So if we treat this with a bulky base like tert butoxide, right, we could do an elimination reaction. To this one, you remember what the name of this compound is? Styrene, good. And then from here, we could do any of our electrophilic addition reactions, right? We could add, if we added HBr, we'd go right back to where we were. We could use hydroborations. We could do just for fun, we could do a hydration reaction. Right, so what would that give us? An alcohol, right? At which position would it go to? To the benzylic position. All right, so we could get an alcohol here, and then we could oxidize that alcohol. Yeah.
Wouldn't you just do the alcohol instead of the elimination too? And that just the bromine good?
You might be able to do that from here. If you used hydroxide, you might run some risk of elimination, but you could probably just do an SN2 substitution on that one, because the benzylic position is a pretty stable position for cation, right? So I think you could do just a direct substitution from there. We could also do an oxidation from this point. So I heard that in Henge's section, so did you guys ever hear of this oxidizing agent, PCC? Yeah, okay, so this is a weak oxidizing agent, so that would oxidize it to the ketone, like this. Right? You can also use, in this case, so another reagent for this is manganese dioxide. And so this is especially good for oxidizing either benzylic or allylic alcohols. All right, so it won't oxidize in just another primary alcohol somewhere that's not at the benzylic or allylic position. Okay, so it's selective about that. All right, so we can do various things here too. All right. There's a new reaction, though, that I'm going to show you right now, too, though. All right, and in this reaction, what we're going to do is we're going to treat this compound with a strong oxidizing agent. So we could either use, like, chromic acid, all right, or another way to... Essentially, to make chromic acid is to use this sodium dichromate and hydrochloric acid. So that makes the same thing, but sometimes you'll see it in the book listed there. Or I think Sapling actually sometimes uses potassium permanganate in base. And for this reaction, they then add acid afterwards. I'll show you why in a second. Okay, so this reaction is kind of surprising, probably, in that it oxidizes the side chain there, and it oxidizes it all the way to a carboxylic acid. So we lose a carbon in this process if we start with ethylbenzene, which is probably just as formic acid or carbon dioxide or something, okay? So why would, under these conditions down here, if this permanganate, basic potassium permanganate oxidizes this, why would we have to add acid in the end? So would we get this form of the acid if it was in hydroxide? No, what would we get? Right, we'd get the conjugate base, right? So in basic conditions, remember this carboxylic acid would be as its conjugate base. So they're adding the acid here just to reprotonate that acid, okay, to get its acidic form. Okay, so this reaction, we can get to this benzoic acid from ethylbenzene. We can actually get there from toluene as well. Okay, so it's still just oxidizing that benzylic position. We could even get there from oxidizing isopropyl benzene. Okay, but if we had butyl benzene, then it doesn't work. Okay, so what's the difference between these? Right, there needs to be a hydrogen on the benzylic position to be able to oxidize it all the way to the benzoic acid. Okay, so this one's different because there's no hydrogen at this position. Okay? In fact, you can also, if you had this in some other way, we made this on the last slide, if you had this alcohol, if we did use these same conditions, it would also oxidize up to benzoic acid. We'd lose one carbon. Okay? Let's think of what we would get if we had something like this. So we've got a benzoic acid with a cyclohexane ring attached to it, essentially fused onto it. And we used chromic acid. What would be our main organic product?
Would it be the carboxylic acid, and then you'd have a prolyl group coming off of the adjacent position?
So one suggestion would be, so what would we have at the other position?
Ethyl group.
Ethyl and a propyl. No, actually what it's going to do is just like it did up here, even if this was a longer chain, or even, I showed it with ethyl, but it could be propyl or longer, and it would still oxidize at the benzylic position to give a benzoic acid. So in this case, what we essentially have is like two alkyl groups. So each of those alkyl groups is going to get oxidized at its benzylic position. All right? So we're going to get a carboxylic acid at this position, and we're going to get another carboxylic acid at that position. Okay, so we get this dicarboxylic acid. Yeah?
Is that failure reactive? So could we take the water away from that and make an ester type of compound?
Okay, so the question is this one pretty reactive? Could we essentially remove a molecule of water? So we'd be going to, you mean something like this? Is that what you mean? Yeah, so this is maybe possible under certain conditions. This one is not really an ester. This is what's called an acid anhydride, meaning it's lost water. The problem is that the anhydride is much more reactive than the dicarboxylic acid. So it's much more prone to going this way than going that way. But I think if you can use something like that they would call a strong dehydrating agent, essentially something that can suck up water and get it to go that way and not have any extra water to drive it back the other way, then these kind of structures can be made. All right? So we can convert alkyl groups on benzene rings to carboxylic acids. Yeah?
So would a byproduct be ethane in that reaction too?
In this bottom reaction? No, I don't think so. So the question, would you get ethane? I think you would get some other, I'm not exactly sure what it would be, some other more oxidized form than that, though, I would estimate under these kind of oxidative conditions. All right? All right, so the last one is to put an acyl group on there. Last time I taught this course, we actually talked about all of the carbonyl chemistry before the benzene chemistry, so then there was all kinds of stuff we could do to this. But so far, all we can really do is just reduce this to the CH2 group, right? So we said that we could do this with H2 palladium on carbon, and then we had the two other, the Clemenson reduction and the, what was the other one? The Wolff-Kishner, exactly right. So we could just do this reaction to convert that ketone down to a CH2 group, all right? So these are basically the types of modifications that we can do once we have a group on there, all right? So let's go on and look at what happens if we try to put a second group on, all right? So what consider to do that, all right? So two things that we're going to consider. One is, if we have one group on there, if we have a mono-substituted benzene, how does that substituent affect the reactivity of the benzene? Okay? Does it activate it? Or does it deactivate it? In other words, does it make it more reactive, the benzene even more reactive, or does it make it less reactive? All right, so we're going to look at that. And then the second thing is if we have one group on there, where does the second one go? Does it go ortho or meta or para to the first group, right? Because we have three possible isomers we could get with two groups attached. All right, and so some of these different groups are going to have what we'd call different directing abilities. Okay? So let's just generalize it first. Okay, so here's benzene in the middle. And I've kind of put these two abbreviations on here. EWG is going to be for electron withdrawing group. And EDG is for electron donating group. Okay, so for electrophilic substitution reactions, what role was it that the benzene played? Okay, it reacts with some electrophile, right? So what role does the benzene play? It's what? The nucleophile, right? So it goes like this. So the benzene is the nucleophile. So is it going to be more or less nucleophilic if you have something that's withdrawing electron density from it? It would be less, right? So if you have an electron withdrawing group, it's going to somehow be withdrawing electron density from the ring. It's going to make it less nucleophilic. Okay, so this would be less nucleophilic. It would make it less reactive. All right, it has less electron density in it. It's a weaker nucleophile. What if we have an electron donating group? It's going to be a stronger nucleophile, exactly right. So this is going to be pushing electron density into the ring. So as we bulk up the amount of electron density, it makes that benzene more reactive. Okay, so this is going to be more nucleophilic, more reactive. Okay, so those are the general trends that we're going to look at. So let's groups on here and let's decide whether they're going to be activating or deactivating. All right, so all of these are going to be compared to benzene, right? So here's benzene by itself. And so we want to know whether the new ring is going to be more reactive or less reactive. Okay? So what do you think if we have a methoxy group on there? What's this molecule called anyway? anisole, right? Licorice smelling. Right, so is this methoxy group, is that more of an electron withdrawing group or an electron donating group? Donating, right? So the oxygen can do both, right? It's more electronegative than carbon, so it can pull away electron density as an inductive effect, but it's much better at donating electron density using resonance. Okay? And so this is basically a strong electron donating group, right? So should this activate it or deactivate the ring? Activate the ring. All right. What about a nitro group? Is that going to donate or withdraw? It's going to be an electron withdrawing group. So many of the electron withdrawing groups are kind of in this same form here, that it has some atom here that has a pi bond to a more electronegative atom. So if it does, then it tends to withdraw electrons out like this. Okay, so this is a strong electron withdrawing group, and so this is a deactivator. All right, what about aniline? What about the amine? Donating. Do you think that that's going to be stronger or weaker donating than the methoxy group? Weaker? Why?
Stronger because it would rather have a positive charge.
Right, it's actually a stronger electron donating group because when you form the resonance, it puts a plus charge either on, in this case, it would be plus charge on nitrogen. Over here, it would be plus charge on oxygen. Nitrogen being less electronegative or more electropositive can better hold that plus charge. Okay? So this is also a strong electron donating group, so it's an activator. All right, what about the lower left? This is called an amide. Withdrawing? Is that what everybody thinks? No? So what's on the nitrogen that's going to play a role? Right, there's a lone pair. Right, and so what does that suggest? Yeah, that it can donate those electrons into the ring. Like this. All right? So do you think, so if this is an electron donating group, let's compare this amide with aniline up here. So which one of those, the one on this left or the one on the right, which one do you think is a stronger electron donating group? How many people think that this amide is a stronger donating group? Raise your hand. One. How many? Two. How many people think the aniline is a stronger donating group? Okay, more people are voting for that. Why do you think that aniline's a stronger donating group? Mostly I just hear a bunch of mumbling out there. Okay, so you're right. The second people are right. And the reason is that this non-bonding pair here has a competing resonance out to the oxygen. All right, so its kind of loyalties are split between donating electrons into the ring and donating electrons out to the oxygen. So that oxygen of the carbonyl is pulling some electron density away from the nitrogen, making a weaker donating group. Okay, so this is still an electron donating group, but this is weaker than just having the aniline, just the NH2. All right? All right, what about the ketone? Donating or withdrawing? withdrawing, right? Because that's kind of the same form as this nitro group. It has an atom with a pi bond to a more electronegative atom. So this can pull electron density out like this. Okay? So this is an electron withdrawing group. What do you think about a chlorine? Withdrawing? So chlorine does have 3 non-bonding pairs of electrons, right? It could do either, right? So this can donate this way, but it's more electronegative, so it can pull electron density out this way. And it turns out that these halides kind of sit right on the fence here. So they kind of do both of these. So for activating and in deactivating, we essentially have this inductive effect. So the inductive would be an electron withdrawing effect, right? So that's just because chlorine is more electronegative, it's pulling electron density out of the sigma bond. And we have resonance, which is electron donating, all right? So in this case, turns out for activating and deactivating, the resonant, no, I got that backwards. Ding. The inductive effect is stronger as far as activating and deactivating. So we call these halogens a weak electron withdrawing group. It's a weak deactivator. Okay? What about an alkyl group? Do you think that donates or withdraws electron density? Donates, right? Just like we've seen before, alkyl groups can donate electron density to carbocations and make them more stable, right? And so this is a weak electron donating group. All right? So let's look at a table here and these out. So if you can see this. All right, up at the top are the most activating, okay? And all of these groups are essentially things like this, where they have some atom attached to the benzene ring that has a pair of electrons that it can donate into the ring like this. All right, so notice, if you can see this, these include amines, right? Whether there's 2, 1, or 0 hydrogens on them, it doesn't matter so much, or alcohols or ethers. Okay, all of these are listed as being strongly activating. Okay? The next ones down, the moderately activating, are ones like that amide, where we have this Y group here, but we have another carbonyl on there. So these are like the nitrogen, or it would be an ester if we have the oxygen, if this Y was an oxygen. And this is the ones that can donate like this, but they have the split loyalty. It's also donating electrons over to the oxygen. Okay, so these are the moderately activating groups. All right, the weak activating groups are things like just alkyl groups, or if we have another benzene ring, or if we have a pi bond. So those are weakly activating. Let's go clear down to the other end. The strongly deactivating groups are things that have that either have some nitrogen like this. Well, a lot of them are with some nitrogen with a plus on it. Okay? And that plus can either be, this can be some kind of quaternary ammonium species or the nitro group. So the nitro group also has a plus on that position. Okay? And then we also include in here a sulfonic acid and even a nitrile. All right, and then the moderately deactivating are all the ones with carbonyl groups. Okay, and then weakly deactivating are the halogens. Okay, and this is kind of an interesting one here. So they've put this in order, if you can see it. So it goes from fluorine to chlorine to bromine to iodine. All right, meaning that iodine is more deactivating than fluorine is. Does that make sense to you? No. Would you think it? Why not? Right, fluorine's much more electronegative, right? So you'd think that maybe that the fluorine would be the most deactivating. But there's two things going on here like we were talking about. Okay, we have, let's just put these out here. Iodine. We have an inductive effect, right, which is pulling electron density away, and we have this donating effect through resonance, right? It turns out that even though fluorine is stronger inductively, it's also better at donating because it's essentially on the same energy level. Fluorine and carbon are on the same level of the periodic table, so they're just about at the same energy level. So here, fluorine is a better electron withdrawing group, but it's also better donating. Okay? Iodine really doesn't withdraw electrons that much, but because has so many bigger, more shells of electrons out there, the energies and the orbitals don't overlap very well with the benzene ring. Okay, so it's a worse electron withdrawing group, but it's also a worse electron donating group, right? So it just kind of ends up in this order. It ends up backwards because fluorine is actually better at donating than you would think it would be, okay? All right, so what we want to know here is just we want to be able to recognize the general order of these. And so if we look at two groups, we want to be able to know, is that an activating, deactivating group? Is this one stronger than that one? But we can fit it into these general classes, okay? Okay, so we can demonstrate this activating and deactivating, or the same kind of process, by looking at the acidity of a couple of different aromatic types of groups here. Okay? So, all of these compounds are based upon this one here, right? So this is phenol. All right? And so we're looking at the acid-base chemistry. And we want to decide whether these other groups are going to be stronger acids or weaker acids. So the pKa of phenol is 9.95. It's not a great acid, but it can function as an acid. So when we want to consider acidity, what do we usually look at? The stability of the conjugate base. So let's think about these conjugate bases. All right, so for phenol, it would be this phenolate anion, right? And what do you think about this as an anion? Is this stabilized in any way? Yeah, right? The electrons on the oxygen can be donated into the ring, right? So we end up with a bunch of different resonance forms here that look like this, with a minus now over here, right? And we could do that again over to here. right? Oops, I can't fit this in here. I'll put them here. Minus down there, right? Or we could bump it up the other side, okay? So we want to know how these other groups can affect the stability of this conjugate base. All right, so what do you think if we have a para-nitro group? So let's draw its conjugate base. We'll draw the whole nitro group out. Minus, plus. All right, so how's that nitro group going to affect the stability of that anion? Is it going to make it more stable or less stable? Less stable? More stable? One of those. Okay, so what is a nitro group? What did we say? Is it electron donating or withdrawing? It's withdrawing, right? So we already know that this oxygen likes to donate electrons into the ring. All right, so if we're pushing electron density in there, and this is an anion, are anions usually stabilized by electron withdrawing groups or donating groups? Which? Withdrawing groups, right? An electron withdrawing group is going to spread that charge out even more. All right? So with this conjugate base, we can have all of the same resonance that we would for this phenolate anion. So we got all the resonance around the ring, but in fact, we can end up with even more resonance. All right? So let me show you that. I'm going to do this in 2 steps. I'm going to bump that one there, and then I'm going to bump this one right over to here. And I'm going to draw this resonance form. And right now we have a non-bonding pair and a minus charge on this carbon right where next to the nitro group. Okay? So from there, we can continue on around the ring, but is there any other resonance that we can do? We can do resonance. We can share that electron pair onto the nitro group. Okay. All right, we can have these double bonds here, but now we have a double bond going out to the nitrogen, and we have an O minus and an O minus and still a plus on the nitrogen. Okay, so this is an additional resonance form that the conjugate base of phenol does not have. Okay? So this is an added resonance. And this additional resonance stabilizes this conjugate base. And so what do you think that's going to do to the pKa? Is the pKa going to be above or below 9.95? It's going to be below it, right? This one goes down to 7.15. Okay, because the added resonance stabilizes that conjugate base even more. Okay? So what do you think if you have that nitro group on the meta position instead of the para position? Is it going to be just as good? No? Why not? Right, it's not going to have that added resonance. All right, so the pKa of meta-nitrophenol is 8.4. Okay, so it's still more acidic than phenol, but not as much as para-nitrophenol. And so the reason was, if we look at the conjugate base here, and we try to do our resonance, we can go to this spot, right? That would put it here. have a double bond here and here. Is there any way to move that pair of electrons out onto the nitro group? No, because if we do try, we're going to move these electrons over here, but then there's no way to bump them out onto the nitrogen group. It's going to go right past over to here. Okay? So this one does not have any added resonance. No added resonance. So why is it more acidic then than phenol? Right, it still has some inductive effect. It's still pulling some electron density away, but not through resonance. Okay, and resonance is usually stronger effect. So this one is less. Okay, so what do you think if we have a methoxy group?
Have a higher pKa.
A higher pKa? Everybody agree?
Yeah.
Yeah, so it goes up to 10.2. Right? Because remember we talked about the ether wants to donate electrons into the ring. And if you donate electron density to an anion, it makes it less stable. Okay, so we could have this, OCH3, right? Because this one wants to donate electron density this way. This one wants to donate electron density this way. Right? And so this is going to make it less stable. Okay? All right, let's just say, okay, the next one, chloro, goes to 9.38. Okay, so it's a little bit deactivating, just like we said before, weak deactivating. The one with the methyl group, 10.3, so that's donating a little bit, makes the anion less stable. Okay? Because this one was a weak deactivating electron withdrawing group, weak electron donating group. Okay? Does that make sense? Okay, so this is kind of just a demonstration of the electron effects. All right, so this is all with carboxylic acids. I'm not going to really go through all of these. Let me just put up some of the pKa's. All right, so if we have a para-nitrobenzoic acid, it goes to 3.44, right? So is there a way for benzoic acid to, here, let me do this in blue, to delocalize the electrons on its conjugate base into the benzene ring? No, it can't really do it, right? All it can do is have the resonance that goes between these two oxygens, right? The benzene ring is actually a little more electronegative, so it just has an inductive effect like this. And if we put electron withdrawing groups, it increases the inductive effect is all. All right, so let's just see if we fit the trends, 3.47. In this case, it doesn't really matter whether it's para or meta. If we have a methoxy group, it goes up a little bit. I don't know that one. And this is 4.34, so that goes up a little bit as well. Okay, so it follows the trend, but because there's no added resonance, the differences are quite small. All right, what if we have these conjugate acids of aniline, right? So in each of these cases, too, our conjugate base would be neutral, but there's a pair of electrons on the nitrogen that can be donated into the ring like this, just like we saw with the phenolate. Right? And so what we see is basically the same trends. If we have the para-nitro, it goes way down. Meta-nitro goes down a little. If we have, all right, so these are electron withdrawing groups. If we have electron donating group, like methoxy, then it goes up. So it's just all the same trend. Okay? All right. So, what was I going to say on this? Is basically just what we saw before. All right? So the next thing we're going to do is look at directing. All right? So we're going to have two groups, really. We're going to have some that are what we call ortho-para-directing. So we can't really direct just to ortho or just to para. It'll go to both of those. But there may be some other effects that we'll talk about. And then there's going to be meta-directing as well. All right? So we'll go over this tomorrow.